Hello, everyone. I'm Yiming, and this is Zaifeng. This is Qitian. We are from 360 Network Security Research Lab, and today we are going to talk about how we use our massive DNS data to do real-time DGA malicious domain traffic analysis. First, some quick facts. Currently, we provide our DGA data feed at this URL. That DGA feed updates once every day, and that's a TXT file actually. The file itself is about 70 mega big. It has more than 1 million DNS entry in that file, so it's a fairly large DNS blacklist actually. And in our feed, we're tracking right now 38 DGA families with 375 DGA variants. And our DNS platform, on average, we see more than 5 million DNS queries looking up for those malicious DGA domains, which means these DGA family are still fairly active. Right now, we have subscribers from more than 50 countries pulling the data. The feed itself is free. You are welcome to use it however you want. There's no charge for that. And actually, if you go to our website, we have more free service to the security community. For example, we run DDoS Mon. It's basically a DDoS monitoring traffic project. It's also free. We also have ScanMon, which tracks network-wide backbone scan traffic. We also have some other open data, so you guys are welcome to go there and take a look. Today I'm going to go through some background information first, then Zaifeng is going to take over. He will talk about how we start from the raw PDNS data, and from the data to narrow down to a highly suspicious DGA domain list. Then Chitar will talk about how we pair those highly suspicious DGA domains to real malware sample in our sandbox. We probably don't have enough time to talk about blocking experience, but we'll see. We all know most malwares, they need to have some kind of mechanism to talk with their C2s, command controllers. Most malwares these days, they use hard-coded C2s. By hard-coded, we mean it's either fixed IP address or DNS name. Here, a very good example is the WannaCry. We all know this year, in May this year, WannaCry made some really serious damage. I think just in one day, that ransomware infected more than 200,000 computers, and more than 100 countries will have infection. If we take a look at the source code of the binary code of WannaCry, we can see that kill switch domain there. It's clear text. It's not encrypted, so everybody can see right in the spot that there's something going on with the domain. And I guess that's why it only takes a few hours after the code got released for a security researcher to figure out this is a kill switch domain and registered it, then sinkhole it. If WannaCry author did use like a DGA, it might take security researcher maybe days to figure out what the real C2 is going to be. So DGA. DGA stands for Domain Generation Algorithm. So basically, by using DGA, that means the C2 is not hard-coded anymore. And the C2 are generated by the malware's own algorithm. And normally, when we're talking about C2 here, we're talking about not just one C2. Malware can generate a whole bunch of C2s and only pick one to register it, and that malware will work. A good example here, I'm not sure if that's clear enough for you guys to take a look, but this is a DGA domain generated by a malware called NACAS. On this DGA botnet will generate 2,048 domains every 3 days. That's a long list. And on the left side, you can see that's some of the domain is generated on November 21. On the right side, some other domains it generated on November 24. So if you take a close look, you will notice a few things. First, most of the domains have this return code, error code E3. In DNS, that means NX domain. Domains not existed. Basically, the malware author didn't register these domains. But also, see the red marked one? On both diagrams, you can see there's one live DGA domain and got registered and was assigned IP. There's also another thing. If you take a look at the TLD, you will see that the TLD is just all over the place. For example, we have .ga, .biz, .taiwan, .us, .russia, .japan. So let's see, if you're a security researcher and you want to register and sync all these domains, it's going to be really difficult because you have to talk with DNS registrar all over the world and also pay a lot of money. Remember, we're saying this botnet will generate 2,048 domains every 3 days. So that's about the DGA. Another piece of this is the passive DNS. For those who are not familiar with passive DNS, you can think it as a kind of DNS database with all the history record. Here, a good example here, nanog.org. Just from the output, we can see some key elements here. For example, the first column is the first thing time. The second column is the last thing time. Also, we have like hit number, the domain was asking for, what type of DNS record that is. Here is the A record, and what's the IP address was assigned to the DNS name. For example, the first line here, from late 2014 to earlier this year, NANOG was pointing to this 50.31 IP address. And see the second line, from earlier this year till now, NANOG is pointing to this 104 IP address. Another example of PDNS, see here, blanytrad.com. Again, this is only part of the whole screenshot, but you can tell that basically these domains changing IP all the time. This is a very typical fast flags domain. Normally, this type of domain is up to no good. It's really safe. It's safe to just kill the domain. So passive DNS has very great potential in security community, and more companies are starting to using it. And that's why we run our own passive DNS system. It's a passivedns.cn. And also, if you're a security researcher, you can go there and apply account. It's free. And the platform currently covers more than 10% of all Chinese DNS traffic. And on average, we see every single second, we see more than 1 million DNS queries per second. And also altogether, we have 15 billion plus RSS. And with that, I'm going to give the mic to Zaifeng. He's going to talk about how he starts from the raw DNS, passive DNS data, and then to narrow down to a high potential DGA candidate list. There's one thing I have to say that probably is pretty obvious. You guys can tell that we are from a non-English speaking country. And I believe actually for Cheetah, this is first time ever doing English talk ever since his college time. That's like 20 years ago. We thought about that. So we think maybe it's better they can read from their cell phone note. I'll make sure they can read it slow, so it should be easy to understand. Yeah, thanks.
Okay, thank you. How to find the high suspicious DGA domains from passive DNS? First, we need to get all the daily new domains. Basically, we are only going to focus on new domains that showed up in the last 7 days. And domain SLD are on the Alex top 10,000 list will be dropped. We also use some other quick filters such as filter out the Wireshark, filter out the wildcard domains. As a result, instead of dealing with all the raw data, we only need to work on a million as a start point. The result of the above step will have some noise. For example, here, big CDN providers such as Akamai and Cloudflare, and all kinds of DNS blacklists, such as Spanhouse and SURBL. Okay, some other common cases. Look at the top one. It looks really strange, but it's not DGA. They are disposable domains from the APNIC DNS test.
Makes sense, right? Ring a bell? Yes.
The bottom two cases are from two DDoS botnet family. The left is Alkanaut and the right is Mirai. These domains are used for DDoS attack. They really look like DGA, but actually they are not. So we have get rid of the obvious noise, and then we are going to go into the most important part here, to cluster the DGA domains. The theory is pretty simple. DGA domains generated by same mobile family should go together in same group. There are two dimensions can be used. Dimension one, time. When mobile runs, it will keep asking DGA domains until it finds one that is resolvable. Dimension two, client. Clients infected with the same DGA family should ask for some domain names in same time window. After this step, the amount of data we need to focus on is greatly reduced. Okay, let's talk about more details. We will do time-based clustering and client-based clustering. For time-based clustering, we use 1 hour time interval to group together all domains accessed by same client. For client-based clustering, it requires 4 steps. Step 1, generate domain name IP matrix named A. Step 2, calculate the transpose matrix of A named A transpose. Number 3, get the domain similarity matrix based on client requests. B equals A multiply A transpose. The greater the value of element of B, IG, the higher the domain name I and the domain name J coincidence. Last step, using the Louvain algorithm for clustering, we set a threshold, and the algorithm groups the high similarity domain names together, so every domain gets sent into a particular cluster. Let's take a look at an example. Okay, this is the example. This is a diagram of client-based clustering. In matrix A, D means domain, and IP means client IP. Value 1 indicates the domain has a DNS query from the corresponding IP. 0 means no query. In this example, we can see that the element value of matrix B is the coincidence number of client IPs between two domains. Thus, based on the client dimension, the similarity of D1 and D2, three there in the green box, okay, is higher than D1 and D3, 1 in the yellow box. Okay, then we convert the matrix B into a graph, set a threshold such as 3, and only save the edges with the weight greater than or equal to the threshold only. So the 4 domains will eventually be grouped into 3 clusters, D1 and D2, D1 and D2 in one same cluster. D3 and D4 are separate, each in its own cluster. Okay, here is what the result looks like. It is still a very long candidate list. For example, this cluster is a typical DGA domain. DGA domain names. It's a configure mobile. The cool thing here is that all the configure domains were successfully grouped together without looking at the configure code. We don't reverse engineer it. Okay, that looks good now, but again, we are going to see noise. For example, this cluster, they really look like DGA, but all of them are actually hard-coded in this mobile, so they are not DGA. You can find the mobile sample through the VerseTotal link. So another example, this cluster, these domains are linked with each other. We call it link farm. You can see the right picture. They linked each other together. They are for black hat SEO, used to bump up their search ranking. So we are going to apply another layer of rules. We are only select the domains that only consider SLD, second level domain, and top level domain. And the length of second level domain needs to be more than 5 letters. And every domain names our data has less than 5 DNS records. Also, for each cluster, the ratio of DNS negative answers such as no such domain should be greater than 20%, and total DNS domain for each cluster is greater than or equal to 4. After this operation, the data reduced to 10,000. Okay, the result looks much better now. So we are looking at the list about 10,000 high suspicious DGA domain. It is relatively safe to use this list as a potential blacklist, but we want to give it even further. We will want to pair the DNS domain to mobile samples so we can absolutely sure. And Qitian will talk about that. Thank you.
Thank you. My job is to pairing the DNS names to MDFIs. We run our own sandbox every day. We run more than 100,000 samples from VT, and even more samples from us in our sandbox. The result is something like this. You can see on the left side is the MDFIs, and on the right side is the DNS names that MDFIs are asking for. For every suspicious domain, there are three pairing possibilities. First, the domain has an undefined match and is already marked by someone as malicious. Second, the domain has an undefined match, but nobody has marked it. In this case, we will need to reverse engineering, and this is very labor intensive. Third, the domain has no undefined match. We can do a few things, but there is really not much we can do here. In general, DGA can be divided into two categories. One is TID, the other is TDD. We will talk TID first. TID stands for time independent and deterministic. That means the TID DJ will generate same domains all the time when it runs. Here is an example. Remnant DGA generates exact same domains in January and in September. The time is different, but the two lists are exactly the same. Among the 38 DJ families we know, the TID DJ accounts for nearly 30%. We will take Remnant DGA, for example, to show how we locate malware sample in the TID case. Let's look at this cluster. Note the SLD is always within a length of A to 19 and consists of A to Y. 0 is always missing. TLD is always .com. And with time goes on, the infected clients always query the same FQDNs, so it look like a TID DGA. Searching the domains in our DNS undefined database, and we got a bunch of undefined. Through VirusTotal, we know that this sample was submitted and marked as Remnant, a known DJ family. So these suspicious DJ domains are generated by a new variant of Remnant DGA we have not identified before. And now we can mark it successfully. Let's recap. We start from the highly suspicious TID DJ cluster. You use DNS undefined pairs to locate the malware sample, and then reverse engineering and figure out the algorithm. Then we can confidently generate domains of this new variant. Now, let's take a look at TDD DGA. TDD stands for time-dependent and deterministic. That means, basically, TDD DJ generates different domains at different time. Here, running a TDD DGA samples in sandbox in different time. And we can see the domain list captured by Warsack is totally different. The good thing is, although the domain names change all the time, the domains generated by the same family will share some common pattern because the algorithms share the same logic. So can use fuzzy match later on. Let's take a look at this table. The first slide, where root generate 10,000 domains per day. TLD is always.com, and SLD is fixed length of 6 letters, always from A to Z. The last one, say cleaner, only generate 1 domain per month. TLD is always.com, and SLD length is within 11 to 13. Always use letter A to F and the number 0 to 9. Among 38 DGA families we know, TDD DGA family account for nearly 70%. We will take China D as an example to show how we locate malware sample through fuzzy match. On August 7 last year, this cluster came up. The FQDNs in this cluster look like this. In the following few days, we noticed that the infected clients of this cluster started to query a whole bunch of different new domains every day. The list of domains are not the same each day, but the domains they asked for share similar pattern. So it may be a TDD DGA. Look at the domains in this cluster. We can extract some features. They have 7 top-level domains: org, ru, cn, net, and so on. And the SLD is always 16. And SLD consists of the letter A to Z and the number 0 to 9. Then, based on these features, we searched the sandbox DNS M-defined pairs database, found that some domains share very similar features, and they are generated by a single sample. Through Google search, we found the Malwarebytes blog. They have analyzed this sample and named it China D, but the article did not mention anything about the DGA. So we create a new DGA family and named it China D. Recap. We start from the suspicious DGA cluster, then figuring out naming pattern and locate suspicious amplifier through fuzzy match, and then reverse engineering and figure out the algorithm. Then we can confidently generate domains of this new family. Thank you.
Yeah, I think we're running out of time for the last section, but good thing is the last section is pretty simple and easy to understand. You guys can just read the deck, but I do want to see one more thing here. Oops. Right now we have this GitHub repository. So on this repository we have suspicious DGA domains without MD5s. We also have some MD5s. We haven't figured out the algorithm yet. And also we keep a list of benign DGA applications, which means the application is not bad, but they just have this DGA active behavior. So for security researchers, you're more than welcome to go take a look. And if you can make contributions, that's going to be great. With that, any questions?
Kevin Bloomberg. A lot of the work you've done points to an interesting way of identifying that's reproducible. It takes you time to figure out the next one, but you seem to be reproducing the way they are generating the domains consistently. Is this something that the registries and registrars should be using in their algorithms for fraud and detection? And is that something that you're working towards? Or you're looking at a higher level, you just expect these will be created and other people are then going to use them? Should it be stopped at the root? I don't mean the roots, but at the root cause rather than after the fact.
Right. As I mentioned before, right now our focus is mainly on producing the data. We have more than we have people from more than 50 countries pulling the data. Right now our focus is just mainly producing the data, but we haven't worked with any registrar to do anything yet. Yeah.
Thank you.
Any more questions? Okay then, thank you very much.
Thank you.